Thank you for letting me the opportunity to talk here. Yes, this work is a joint work with Inma Baldoma, also in Barcelona. Well, the generalized standard maps we want to consider in this work are, standard models are maps of the form xy goes to y plus some function where, for instance, x and y are in R2. Also, we can consider the case where this is defined on a cylinder. Several known examples of these types of maps are, for instance, the Chirikov standard map. And this is well known. Also, the Dienon map. And, well, the other maps of these types, the Macmillan map. I will make more comments on them later. We are particularly interested in some problems related to these maps. And
F is any smooth function? What is F?
F is a function of x and h. I'm going to put hypothesis right now. Okay, so hypothesis. I'm going to call H1 is going to be a set of hypotheses. The first one is that F is going to be analytic in the neighborhood of x equals 0. It could be also periodic on x, but let's assume for now that this is we are in this setting. I assume also that the origin is a hyperbolic fixed point for this map. And the parameter h is chosen in such a way that the Lyapunov exponent of the origin is of the form is of this form. I mean, h, the parameter h is exactly the Lyapunov exponent of the origin. Okay, so we are interested in the case when h is small. So the origin is a weakly hyperbolic. Well, under these assumptions, what we have is, well, it's standard fact. We have that the origin is hyperbolic. And the invariant manifolds of the origin admit what we call, or what is usually called, natural parametrizations. Can be parameterized by functions Is it? This, all the maps of this type are conservative. Oh, yeah, this is, sorry, maybe I should have tell that. In fact, this, for any f, this is an area-preserving map. It does not depend on f. In fact, well, this is one of the main reasons that we consider this this kind of map. It also has other properties. Well, if I need them, I will. But this is a very rigid form, of course. Okay, but it is used as a model, a simpler model of other phenomena in differential equations. So the invariant manifolds, for instance, the unstable invariant manifolds admit a natural parametrization. I mean, something like these, where these functions are going to be analytic and that satisfy this condition, they conjugate the action of the map with the translation on T in H, where H is just the Lyapunov exponent. And if it's going to be, this only says that the graph, or this curve is invariant, and if I add this assumption, then I have the invariant unstable manifold.
But it's the same H?
It's the same H. Yeah. This is standard fact. I mean, a very crude way to prove this is for instance, using normal form around the origin. You can put it, and then you have an explicit expression of that, and then you have this. But of course, it's not necessary to use normal form, Birkhoff normal form to get this result. Well, the same, if I put here an S, I have exactly the same with H also.
You have an H in the definition of your map, and you also have an H, the exponent H. Is that
They are the same H. I choose the parameter H to be. I can rephrase this. I take a family of maps.
Yes.
I compute the Lyapunov exponent. I take the logarithm of the Lyapunov exponent, and then I assume that this is the hypothesis that this family of maps is analytic with respect to the logarithm of the Lyapunov exponent. It's just renaming the parameter.
You don't get any problem for H equals 0 with that?
Oh yes, of course, we have a lot of problems. The point is that
Analyticity. So F is analytic in a normal H less than, so it's analytic in a neighborhood, or you would like to take.
in a neighborhood of H equals 0,
Yeah.
yes, it's in all the examples we will have this hypothesis.
But I mean, but if you take the logarithm of the Lyapunov exponent as parameters, maybe you will not get analyticity.
It's true, but it happens in the examples that, yes, of course, yes. Well, I would like to, let me add some more hypotheses, and then I will explain the problem we want to address. Well, this map, if I made some rescaling, I rescale the variables just to show what happens. Rescaling, which is the rescaling, because I never remember. I perform this rescaling with the parameter H here, and well, I should write X tilde and Y tilde, but I forget the tildes again and write again the map, and the map becomes this one plus HY. Yes. Plus something that is going to be H squared, where this F0 is defined simply by, it's the first term in the expansion on H of F. Oh, by the way, maybe I should have told this condition here is equivalent to say that the derivative is, there is a relationship between this condition and the derivative of F, of course, which is going to be this one. So if I do the expansion on H, I mean, this f must start with terms of h squared. This is why I put a 2 here. And
I cannot read what this value is.
yeah. So it means that in H, it starts with terms of h squared. This is what this condition says. And this is why I put a 2 here. And what it says is that this map in these scale variables is a close to the identity map when h goes to 0, because when h goes to 0, I have only the identity. And this suggests that I can approximate this map with simply the time h flow of a 1 degree of freedom Hamiltonians in this, since it is area preserving. And indeed, I can consider the limit flow, which is simply the flow that I would obtain passing this to the other side and dividing by h. Limit flow. It's simply with the certain hypothesis. So without any more hypothesis, I cannot say anything else. And now I assume another thing is that this limit flow, which has a hyperbolic fixed point, has a homoclinic loop. It needs to be more or less this way. Well,
I'm sorry. So, in what sense this is a limit flow? How do you get this equation?
it's just to take the terms of order h. Let me check. I mean, if you have this equation and you consider that the time h map generated by this, you obtain just the first terms here. That's as simple as this. So this homoclinic loop, I assume, is given by proof of this way, and I assume that this parametrization is just the time parametrization. Means that when t goes to minus infinity, I go to the origin, and when t goes to infinity, I go again to the origin. And I can assume, due to the symmetries of the problem, that if necessary, changing t by a translation in t, that x dot of t is even, which simply means that this point corresponds to t.
The limit flow doesn't preserve area anymore.
Yes, it is. It is a Hamiltonian system. It's a mechanical Hamiltonian system.
Okay.
Yeah. The preservation of area of the map implies that this is mapped. Well, the invariant manifolds of the map we are considering, of course, do not need to I mean, we have this loop, and in fact, what happens is that the invariant manifolds of this map are close to this loop. But of course, well, this is a theorem, but the idea, I mean, of course, they do not need to coincide. I mean, when consider the map, the invariant manifolds do not need the concite. In fact, for instance, if the function f is entire, they must split. They cannot concite. And the problem we would like to address, or at least to say something about that, is concerns about the size of the splitting among these curves. We want to say how much differ these invariant manifolds. What happens, what is known, it's an easy computation that if we expand the invariant manifolds, these functions gamma u and gamma s, the expansion of gamma u and gamma s in powers of h, we consider that expansion, the first order term in h is precisely gamma naught, which is the same for the stable and for the unstable one. This implies that, it's an easy computation, that the rest of the terms of the expansion are also the same for the stable and for the unstable manifold. And what we get, if we try to compute this difference expanding in H, is that the difference, I don't know, I measured the distance somewhere. But anyway, it's going to be of order h to the n for all n. Because the expansion, yes?
Which measurement of the distance do you take?
And
How do you measure
I will say something more precise later, but in any way, you can take, for instance, this angle.
the angle?
For instance, it's not.
There's different way of measuring them.
There are different ways. Yes. For instance, you can use the angle. You can use the area. In fact, the angle is. And the angle is not a good way to measure this difference, of course, because the angle is not a symplectic invariant. It's better to use something that does depend only on the homoclinic point and not on. Depend on the orbit and not on the homoclinic point. And if I take the angle is not going to be the same here than in other points on the same orbit. And I will consider another quantity later. Well, we have this phenomenon. In fact, this phenomenon does not need anything to be analytic. In the case infinity, we have already this. And because if it's say infinity, you can perform all these computations anyway. And now, another hypothesis. I have H1, H2, and H3. I assume that, and this needs the map to be analytic. I assume that this homoclinic loop is indeed analytic in some band in.
I don't quite understand. So this gamma u is the unstable okay starting from that origin?
These are the invariant, the natural parametrizations of the unstable and stable manifolds of the origin. And I measure the distance among them, in between them. And this distance happens to be of order h to the n for all n.
For all t?
No, well, if you fix t. Of course, you have to fix. I mean, t, I put t0. No, of course not, because if they do not coincide, then in the end they're going to be far away. So you have to fix it. Well, I am going to assume that H0 is analytic in fact, this is the definition of sigma naught. If F is analytic, if this map F is analytic, this homoclinic loop is going to be analytic in some neighborhood of the real line. And the neighborhood, the size of the neighborhood, I'm assuming that is sigma naught. So this is where time is. And I'm assuming that for t here, this function is analytic. Then there is a classic result from the 90s, from Dick Simon. They prove that under hypothesis H1, H2, and H3, what happens is that this distance is not only of this order, that it's already is in fact bounded by some exponential. Exponential, something that is exponentially small in h. In fact, that they prove is that this distance, again measured at some point. Let me write the precise statement. For all sigma between 0 and sigma naught, this sigma naught here, there exists sigma, where this distance is less than equal than k sigma minus 2 pi sigma divided by h. So, I mean, the expansion of this function is, of course, of order h to the n for all n, and this provides an upper bound of the difference between the two manifolds, so in particular the area or whatever you want to measure of this.
You need the distance between gamma 0 and gamma s.
Gamma, well, with this symmetry is the same, but I'm saying gamma u and gamma s between the invariant manifolds of the original map F.
But they could split off.
For instance, I measure that at any point here.
So the bound is true even intersection points outside of the strip? Or?
T0 needs to, no, it's true. T0, it's real. I mean, in this picture.
The net distance at the intersection?
No, well, maybe I should say, I did not want to be very precise, but if you want, I can say the area of the lobe between the unstable and the unstable manifolds, for instance, this area that is written here. This area satisfies this bound. Is this, or if I compute the determinant of the tangent, the tangent vectors to these curves, which is a symplectic invariant, this determinant also satisfies this bound, for instance, at the homoclinic point.
But there is a big loop, the first one, which does not satisfy it.
This, no, it's not big at all.
No, the one in the middle.
Oh yeah, but here, yeah, that's why I'm measuring between gamma u and gamma s.
Yeah, but there is a big loop between gamma u and gamma s. The first one.
I don't understand. What?
No,
I mean, they go around the separatrices.
they go around the separatrix.
Yeah.
You mean you have this one, and then you have this. This is small.
Yeah, but you have a big. The separatrix is contained in between them. So the first one.
The separatrix. You mean that goes inside? Sorry, I'm not following you.
So is it true that in the original problem, that unstable, there is a homoclinic orbit you are assuming?
There is a homoclinic orbit in the just for the flow.
So that in the original problem, that unstable manifold doesn't have to close up, right?
No, But if I add this assumption, then for h small enough, the invariant manifolds are close to this homoclinic. So they must intersect the horizontal line. By symmetries of this problem, it means that they must intersect the unstable.
So you might want to measure the distance from this homoclinic orbit in the limit with the unstable stable.
No, we don't. What we want to do, I mean, this is an auxiliary thing that we use to measure the distance between the invariant unstable manifold and the invariant stable manifold. We don't want to measure the difference between of course, the distance between this manifold to this curve is of order, well, h squared. Because, as I have said, this is the first order approximation in H of the invariant manifolds. Well, then I will consider some examples and probably. Another way to deal with this, well, to treat this problem is, instead of writing the limit flow in that way, is to write the equation, the invariance equation here for xu and yu. And it happens that the invariance equation, this equation here, is equivalent to say and it happens that if I expand formally this expression here is nothing else than formally it's applying this differential operator to the function xu. And this is nothing else than h squared times plus O h to the 4. And hence, this also starts with terms h squared. If I only keep the terms on this side and this side of h squared, I obtain exactly the limit flow again. This is going to be. It's another way to write the limit flow. It's just, but since I'm going to deal with this equation from now on, I prefer to write to have only one function and work with this instead of keep x and y. Well, even if the invariant manifolds do not coincide by the conservation of area, they must intersect, and the symmetries imply that they have to intersect on this line. Now I'm going to fix what I'm going to measure. There are several ways to measure the distance between gamma u and gamma s. One possibility is to measure the area of the lobe. If they intersect, this is going to be one homoclinic point. This is the unstable, whatever. This is the stable. The pre-image is going to be around here. this is going to be gamma u, for instance, 0. And this is going to be gamma u minus 8. It's area preserving, and so this point goes to here. There must be 1 in between. And we can try to compute this area. Or we can try to compute what is called the Lasutkin invariant, which is, I give here a precise definition. If I assume that the invariant manifolds are parameterized with natural parameterizations, and in this setting they intersect at 0, then the Lasutkin invariant is the determinant of the derivatives. It is a more or less known fact or accepted fact that under generic conditions, computing this number or this number are equivalent. You can obtain one from the other under generic conditions. In particular cases, it's not proven. Well, for instance, I will try to compute this, or to give an idea of how to compute the Lasutkin invariant. Let me review some known examples. Probably the best known is the Chirikov standard map. It was introduced by Chirikov to study resonances, what happens around resonances. And it's given when I take f of x h to be epsilon sinus x, where epsilon is this one. Well, it doesn't fit on the hypothesis because this is trigonometric, but all these I'm not going to repeat this, but we have performed all these computations in the case also of trigonometric functions, not only in the plane. But probably this was the first example where the splitting was computed. The proof was complete. In this case, the limit flow is just a pendulum, and the singularities of the pendulum are located. The singularities, I mean, is sigma, here, or the closest to the real line singularities of the homoclinic. Are located at I pi over 2. And well, it happens, I mean, it's a lengthy proof, but that the Lasutkin invariant in this case has this expression. It's 4 pi divided by h squared, and we have the exponentially small behavior and a series. This is only an asymptotic formula. This is not an equality. In fact, this series is not convergent. It's a divergent series. But means that if I cut up some time at some place, the error is of order the next term. What I want to point out is that the exponential, what is here, the exponent, is well predicted by von Teximo theorem. It's exactly the number that is written there. Another example where the proof has been carried out is what is called the Macmillan map. The Macmillan map was introduced by Macmillan to study some particle acceleration dynamics, and it's given by, well, the Macmillan map itself, it's integrable. This is a peculiar thing. It's not very common to have maps that are integral, and it has polynomial first integral. So it means that there is no, there is no splitting at all, since there is a loop. But one can consider perturbations of the Macmillan map. In fact, the first to study the problems of splitting in this context use the fact that it was integrable in order to develop a Melnikov integral and then prove that the Melnikov integral provide a good guess. But anyway, if we assume this is B prime, if where we can take this to be analytic. And epsilon tilde is a parameter independent of h and does not need in principle to be small, could be large, or at least of order 1. But, well, then it's not the same. It still is a perturbation because the phenomena happens very close to the origin, and this starts with terms of order I to the 3. In this case, the limit flow, in the case of the it can be written in that way. Of course, it's not in that way. It can be written in that way with a specific f, which is something like epsilon x plus some constant minus positive constant plus epsilon square. And in this way is exactly like latex standard map. And the limit flow is simply a Duffin equation. Is this? And the homoclinic of the Duffin equation has the singularities located also at I pi over 2. Again, the guess would be that the exponent in the splitting is going to be of this size. Well, this is indeed what Seara, Sosen, and myself prove. And we obtain a formula in the following way. If b hat of 2 pi is different from 0, where b hat c is the Borel transform of the perturbation, then the splitting this is also asymptotic, and we have this parameter. This parameter is a reflection that when epsilon tilde is 0, there is no splitting, and then we need this assumption because the first order, the first term here, is exactly this. Well, this is what happens, I mean, with complete proofs. Here in particular, the interest was to find, I mean, this Borel transform is related to some resurgent problems, and well, it's the techniques involved that particular. Some numerical experiments have also been performed. By Gelfrey and Simon. By the way, I forgot to say that this the proof of the standard map was carried out by Gelfrey following this scheme also developed by Lasselkin, who passed away before finishing it. Treschow, in the Cherenkov standard map, Treschow, he had the rapidly suspension, but did he apply to the? I didn't know that. I mean, I thought that because I know his work on with this continuum averaging method. Yeah. Do you mean do you refer to that? Oh yeah, okay.
No, this is problem.
This is?
To standard map.
To standard map, but he applied it to the pendulum, didn't he? Yeah. He had a pendulum with a rapidly forced perturbation. So some numerical experiments where if f is a, and this is a polynomial, epsilon always is 4 sinus symbolic square. Then you have a numerically obtained formula which says simply that polynomial of degree n. Then there is some constant that only depends on n, the coefficient of the plus higher order terms. And rho is precisely the, well, this sigma naught that I have written here is the distance, the distance of the closer singularity of the homoclinic orbit of the limit flow to the real line. So this plays the role of sigma naught. And again, the exponent is well predicted by Fontiximo theorem. This function omega tilde of h can be just simply 1 if there is only one singularity of closest distance. It could be a periodic function of period 1 over h if there are two singularities, or it can be a quasi-periodic function depending on the relationship of the singularities. I mean, it depends. We can have, in the previous example, the closest to the real line singularities, there are only one, but of course there could be more. And then things start to oscillate, and we can even have more, and then we have some quasi-periodic behavior of this element. Of the homoclinic, of the homoclinic orbit of the limit flow. This is where we have to look to see things is just this homoclinic here, which is the homoclinic solution of that flow over there. This is what, in all these examples, governs the behavior, where the singularities are located. The, excuse me?
The homoclinic it's an analytic function in a certain region around the real axis, is that?
Oh, well, it needs to be. I mean, it needs to be because the limit flow is analytic.
Yeah.
And since I'm assuming that it's there is a homoclinic loop, the solution is defined analytically here, and then I can extend around, and I have some width. And this is, I mean, there is some width. So with those hypotheses, there is such a width.
There are no singularities there.
Oh, yeah, no, but there needs to be at least one. I mean, the homoclinic loop cannot be entire. It must have singularities. It cannot be entire because since it's homoclinic to the origin, in this side, in this place, is bounded. In this other place, bounded. And since well, you could see that there is also a period, an imaginary period. So it needs, if it has no singularity, it would be bounded. So it has to have singularities.
Knowing there's some imaginary period helps a lot. Knowing that, okay.
Well, we have recently considered as an example, now I'm going to erase this. Which is certainly academic, but is different from what we have done here. If we consider the generalized standard map, new example. The generalized standard map given by this function is in principle polynomial, then the limit flow is exactly like in the case of the Macmillan map. It's a Duffin equation. And the singularities, of course, then do not change, are here. So one would maybe guess naively that the exponential behavior is going to be the one given there, but this is not true in this case. Of course, that bound is right, but the exponential behavior, I mean the asymptotic behavior, is not given by that formula at this point.
Is epsilon equal h here?
Yeah. In this case, we have computed numerically. There is some constant here. Is this minus pi squared over h, which is the same that we have here. But there is a large correction, which is this one. So there is a exponentially large correction to the size of the splitting in this case. And the constant A has been computed numerically in two different ways. So in particular, the last token invariant is much larger than the naive case, than the naive case. And this suggests that in this case, in this particular case, the limit flow is not a good candidate to approximate the invariant manifolds in order to obtain the formula, and something else needs to be done. Well, I'm running out of time. So where does the inner equation appears? The inner equation appears where one wants to compute this constant here, the constant, well, and all the constants involved in the previous formulas, in the leading term. The leading term, in fact, appears from an equation. It's an invariance, an equation that reflects the invariance of the manifolds. But studies the manifolds where the homoclinic fails to provide good approximations of the invariant manifolds. And if I add another hypothesis now, because I needed to. This is the f that we have previously. And now I assume that each of these fk is in fact polynomial. This is something that is new, is a polynomial. Of degree, let me say, dk. Exactly dk, precisely dk. I mean, it's not a polynomial of degree dk minus 1. And I assume also that this set I'm asking that dj minus 1 that there are some specific case which made this number greater than the other ones, and this set is not empty. If I have this hypothesis, then I can construct the inner equation associated to this problem. And well, under this assumption, we can rescale x in the equation, the invariance equation I have written before. I'm going to write it again. Rescaling means introducing a new variable where alpha is precisely this number, well, the inverse. And then this equation in this new unknown becomes something here, f. But if I let h go into 0, then I obtain something that is not a flow, it's not a differential equation, but because this part does no longer depend on h, but it's also an invariance equation, which is what is usually called the inner equation. Plus other terms. the idea is that the information that we need to prove that the splitting, I mean, that this constant here, in fact, comes from the study of the difference of two particular solutions of this equation here. This has been in the heart of the proof of these examples that I have written here. But what we have also done is consider this in full generality, because there are many examples. And well, we have been able to obtain information about this. I'm going to skip the details of, but it's possible. This change what does this change of variables. By the way, he is in principle one arbitrary complex number, and it's possible once. This is the new time, this is set. This is the complex plane, and this is 0. And there exist functions phi u and phi s, which are solutions, which are defined in this domain here. Which are solution of the inner equation. And whose difference is in this region here. This is an inequality. I want to emphasize that this is not an asymptotic formula. Is given by cyclically. And these psi1 and psi2 are precise functions. In fact, psi1 is exponentially close to the derivative of phi u. I mean, more or less in this expression here, I can put phi u, and I have no error, more or less. And it's possible to obtain bounds of this other function psi2. And this formula means, in particular, look that we are in the lower complex plane, so the imaginary part of set is negative, and k is negative, so this provides, in fact, an exponentially small formula for the difference of these functions when I go down here. Well, my time is over, but the point is that if one can, now I'm way behind, one can prove that the xu, the solution of the invariance equations for the unstable manifold, is a good, well, that this function is a good approximation of xu in this place, in this part of the complex plane, and this is a good approximation of the stable manifold, then the difference of the unstable and the stable manifold is given by this formula. And this is how we have computed, we have performed the numerical experiments using this formula. From here we have obtained the coefficient, and well, and that's it. Thank you.